What is up, YouTube? Adam here. Today we're going to be talking about singly linked lists. The singly linked list is an entry-level data structure, and it's imperative you're familiar with them if you want to truly understand higher-level data structures. Additionally, it brings things like memory allocation and recursion into the conversation, and many foundational data structures, such as the stack, may use a singly linked list underlying their implementation. Today's video won't be such an in-depth analysis. Rather, it's intended to introduce you to the concepts so you can join in on the conversation about things like doubly linked lists, binary trees, and graphs. So let's get started. First, we need to set up our Python file with the skeleton on which we can build. So, a singly linked list is represented in Python as a class. So here we are creating an instance of a singly linked list class. It's common convention to capitalize the first character of a class, as you can see here, but just know you could start a flame war with the nerds if you're overheard saying this is the de facto convention. You should politely direct them to read Clean Code by Dave Thomas, not the Wendy's guy. So what does a singly linked list do? Well, just like an array, a singly linked list stores information. So let's iterate over a list of items and we'll store them in our singly linked list using slist.add. Right now you may be thinking, Adam, you're reading values from an array. Why wouldn't you just keep them in the array? Long story short, singly linked lists offer improved performance when inserting and removing values frequently. Although Python slicing presents a great alternative, you don't know how many interviews I've been asked to manipulate a singly linked list. It's something you don't really need to know until you need to know it. So back to our data structure. How would you view the contents of a singly linked list? Well, convention is to use what is called a runner node to traverse the list. If that didn't make any sense, that's okay, we're going to cover it. But for now, just know in our case, we're going to use the language features of Python to make our lives easier. For now, we'll just put print slist. Besides adding to a singly linked list and traversing it, both of which we're going to cover, we need to be able to remove an item from a singly linked list. So we'll say singly linked list remove, and we'll just take out the number 3. Finally, we'll print the updated singly linked list. With these 3 operations, add, remove, and traverse, you should be able to accomplish 80% of singly linked list challenges. So let's fill out the skeleton for our singly linked list. Now, when you learn how to implement a singly linked list, you'll get a 2-for-1 deal. That is to say, you get to learn an additional underlying data structure, the node. A node is a simple class that contains 2 elements. The data it stores and a link to the next node, which likely also stores data and definitely has a next link, although it may not point to any other node. So what does that look like programmatically? Let's just fill in the constructor for the node to accept data and the next node, and we'll initialize the next node to be none if not provided. So we say self.data equals data and self.next equals next. Now, let's comment out our main to give an intuition for how these nodes are used. So we'll say node equals node, and we'll let the data be 6. And the next node would be a node whose data is 5, and whose next node is a node whose data is 4, and we'll set the next node for 4 to be none. Because we defined our node class with a default of none for the next node, we can just omit passing none in as an argument. So underneath the hood, all singly linked list class is doing is managing these operations for us. We just supply the data to be inserted. Now, remember earlier when I said we traverse the linked list with a runner node? Well, another name for this node could be called a pointer. So let's create a pointer node that points at the head node, or just node in this case. Now, to run through all the values in the list, we can say while pointer is not none, or more abbreviated, while pointer, print pointer data. So the next line is what prevents us from being stuck in an infinite loop. because without pointing to the next node, we would be infinitely stuck on the current node. We say pointer equals pointer next. Now, the runner node will print 6, then 5, then 4. And we know that 4's next node is none, and by assigning a pointer to this none value, we'll break out of our loop. This is how traversing a singly linked list is accomplished. If we wanted to remove 5 from the singly linked list, we could say node next equals node next next. Python automatically handles garbage collection for us, so we don't have to delete the node containing 5. But I'll show you how to do that when we implement the singly linked list class. So now, if we run our program, you can see the node containing 5 has been removed. So let's remove the node from our code base, and we'll comment out the traversal as we'll be coming back to it. Now, in the previous example, we were essentially letting the variable named node behave as what is known as the head node. Every singly and doubly linked list has a head node, so we'll just create one in our singly linked list class and initialize it to none. That's all we need in our constructor for the singly linked list. With the head node in place, we can now add nodes to our singly linked list. So we will just wrap the incoming data in a node and set the newly created node as a head node. If we replace a head node, we need to keep a next pointer to head, and we can throw that in the node constructor. By inserting into the linked list in such a way, we are effectively reverse chaining. That is to say, the values are stored in reverse order. This is functionally equivalent to a stack or insert 0 for Python arrays. The advantage to this approach is a constant insertion time for those who care about big O notation. To store the data in the order in which it was received, it would take O of n time, where n is the number of nodes in the singly linked list. We'll come back to that thought later. Next, let's finish up remove. So, to remove a node, we must first find its location in the linked list, if it exists. That's where the runner routine discussed earlier comes into play. But realize, if the singly linked list is empty, there is no need to continue in the operation. So we can say, if the head node is none, we can preemptively return. So now we can just cut and paste what we commented out and make changes to point the pointer node to the head of the singly linked list. Now, instead of printing the node, we'll compare the node's data to the incoming data parameter. So how do we remove the node? As in the earlier node example, we just need to change the previous node's next pointer to point at the next node's next pointer. But how do we access the previous node? In a doubly linked list, this would be easy, as each node keeps track of not only the next node, but the previous node as well. For a singly linked list, we have to keep track of this node ourselves. So let's fill in the code for our previous pointer, even though we haven't created it yet. And under the assumption that we only want to remove the first occurrence, we end the iteration with a break statement. Now, back to tracking the previous node. The approach to traversing the singly linked list here is what is known as the iterative approach. That is, there's only one function call. However, singly linked lists are often used to introduce a concept known as recursion, or when a function calls itself. Now, I don't want to get too in-depth into recursion in this video, although I will address it in future videos. But we'll introduce the concept here. We will let the initial function call to remove be what is known as a kickstart function. It will ensure the list is not empty and then kickstart the recursive function calls. So what does this look like programmatically? Well, the first part of our function will look the same. Then we'll check if the head node's data matches the data marked for removal. If it does, removal is as simple as changing the head node like so. Head equals head next. So we've now removed the node containing the data marked for removal. There's no need to kickstart the recursive function, and we can simply return from the function call. Now the fun part. We're going to create our recursive removal function. So we'll just go ahead and create our function signature. define underscore remove. It's convention that functions and variables whose first character is an underscore identifies them as not for external use by the API or application program interface. Although in Python, there isn't a way to restrict access to this function. So this is where we will keep track of the previous node in the parameter list for the recursive function. We will say previous, current, and the data for which we wish to remove. So we'll just pass on filling out the function for now and talk about how to call this recursive function. I'll just comment out the iterative removal code, but leave it here so you can keep the big idea in mind. So our kickstart removal function identifies that the linked list is not empty and that the head node does not contain the data desired for removal. So we can then pass the head node to our recursive function as previous and head next as the current node to be evaluated. As well, we need to pass the data indicating this is what we want removed. So you'll hear these terms passed around a lot when dealing with recursion. They are essentially the big three of recursion. 1 is the base case, 2 is processing, and 3 is the recursive case. So what does that mean? Well, the base case identifies that we have finished our recursion and that we're ready to unroll the stack frames or just exit. More on that in future videos. Here, our base case would be that either node is none because we can't operate on nodes that don't exist, and more importantly, if we found the value for removal, we're done. Well, if prev or cur is none, return. If the API's conventions are followed, we only need to check that the current node is not none, as a calling function guarantees the previous node is at the very least the head node. If cur.data equals data, we're done with processing. This is our base case. We just need to set the previous node's next to the current node's next and return. Now, there is no processing in this example, so we just need to fill out the recursive case. In the event that we haven't preemptively returned, we know that cur is not the node we're looking for, but at a minimum, it exists. That is to say, it is not none. So the recursive case mirrors the recursive call in our kickstart function. We say self._remove and then pass the current node as the new previous node and the current.next as the new current node. As well, we need to pass the data we are looking to remove. So that fulfills our requirements to add and remove from a singly linked list. Let's talk about traversing the singly linked list. Earlier in our runner example, we used a pointer to traverse the list. Python has a built-in iterator function that we can use to translate this while loop into a cleaner API. Here's what I mean. If we type def iter we can add our runner code here. So we'll say pointer equals self.head while pointer, and we'll pass for now, and we need to continue iterating through our linked list. We say pointer equals pointer.next. Now, here's where Python really helps us out. We can say yield pointer. This is what's known as a generator function. So now we can use a for loop that more closely expresses our intentions. We can now say for node in singly linked list. We'll say for node in list print node.data, and we'll use a white space delimiter. And we'll do the same thing for the second print statement. So all of the code here meets the minimum criteria for a singly linked list. However, a common operation for singly linked lists is to append data as opposed to adding data. Appending data to the linked list preserves the order of insertion, whereas adding to the linked list reverses the order in a last in, first out manner, commonly referred to as FILO. So the typical implementation is to use a runner or a pointer node to reach the last node. This would be expressed as while pointer.next is not none, or more simply while pointer. However, I'm going to show you how we can use our new iterator method and Python language features. First, we'll create our method signature. I should note, when a function is attached to an object, it is referred to as a method. Anyway, the signature would be define append, self, and data. Firstly, we need to ensure that the head node is not none. If it is, the append operation would be functionally equivalent to adding. So we'll just add the node and preemptively exit. If the head node is not none, then we can iterate through the entire list using our new iter method. We don't really care about any operations, so we can use Python's language features of list expansion and negative indexing to get the last node, and then we'll set the last node's next node to be a new node containing the data. So we'll just append 3 after we've removed it. Lastly, we can clean up how the singly linked list is printed by overriding the dunder or double under str method. It would look like this: return str, and then we'll use Python's list comprehensions and say node.data for node in self. So now we can change the print statements to use our new method. So this is about as Pythonic as you can write a singly linked list. You should now understand how a singly linked list works, as well as picked up a couple of new language features in Python.